Good night, everyone. Mechanics of Material, Chapter 1, Stress. We can see a steel tie bar which is bolted between a double brackets at both A and B. Let's start our problem. The steel tie bar, which is this is our tie bar. We can consider center line as a symmetry of the structure. It is designed to carry a tension force like P is 120, so there is a tensile force of 120 kilonewton and bolted between double brackets. These are our brackets. This is our pin, and these are a brackets, and this is our fixed support at both ends. We do know what the thickness of our steel bar is, which is 20 millimeters. It's given to be 20 millimeters. My bad, the thickness. This is a top view, so the thickness, which is the other side, this is 20 millimeters. We'll show it from different aspect. And then if we do know the allowable stresses like sigma allowable acceptable is 175 megapascal, shear acceptable or allowable is 100, and bearing sigma b, sigma sub b is standing for bearing stress is 350 megapascal. We want to design first the at part A the diameter of the bolt. So this is our pin. We want to know what is the diameter of this one, and the diameter, the dimension b, which is the total part of this part. We'll talk about it, and also height of our steel bracket. We'll go through each of them. So we already know our bracket is in a double shear, so this is a pin in a double shear. We already know that. And the thickness is which is provided like 20 millimeters thick. And we already know this is in a double shear from the side view, from a top view, and also from the side view. We have it like here. This is side view, and this is a top view. And you can clearly see this is a double shear. So if this is a double shear and there is a 120 applied, so 120 kilonewton should be dissect between 260 kilonewtons. So if you want to design the diameter, so we can have a one of these forces like F1 over the area, which is over the area of our pin, which is 60 over a quarter of pi d squared. And we do know the allowable shear is 100 megapascal. Replace it in the equation, looking for the only unknown, which is diameter. Do the math, it just gives you 27.6 millimeters, rounded up in terms of safety factor, and use a diameter of 28 millimeters for our pin over here. Use it like a pin by a diameter of 28 millimeters. And then we have we need to check the bearing stress between the 20 millimeters thick plate and also bolt. So in that case, sigma bearing is P force over T times D. This is our thickness, this is our thickness, and times D is just the bearing stress. So for bearing stress, total force of 120, like if there is a P tensile apply here, there is a P prime, like effect of action and reaction, like a bearing force applied to this part, and That's over 20 times 28. We just calculate the diameter to be 28 millimeters. So if you do so, it just gives you the sigma bearing available is 214 megapascal, and definitely that's less than sigma sub B, which is 350. So that's a checking. Let's talk what if this number like 400 is more than a sigma allowable. We'll talk about it later, but now for our case, that is okay. And then for getting the dimension of B, B is the total of this height. So in that case, sigma is half of P. So let's talk about this part. If this is P prime equal to P, it should be cancelled out by a half of P, which applies at a this area, thickness of T. And if we call this thickness like A, that's applied at A times 20. This is 20, this is A. So sigma is applying there, and half of P is applied, as you can see. 175, which comes from problem statement, is equal to half of total force is 60 over 20, and A is unknown. We are looking for A. And if you do the math, it just gives you A is equal to 17.14 millimeters. And then definitely the total height is definitely diameter of 28 millimeters. We already calculated, and two of these A's. So it just gives us a numeric value of total height of B, which is over here. B is 62.3 millimeters. And to conduct the part C, the dimension of H, we already know what T thickness is. We want to calculate what the H is. We already have sigma from problem statement, and sigma, the total force, is P over THR, applies all over this area, and the only unknown is H. We want to calculate it. If you replace the numeric value, it just gives you a numeric value of H equal to 34.3 millimeters, rounded up, and use H 35 millimeters in terms of increasing the safety factor. Now we have almost all the uh, dimensions, and let's reflect and think about the problem. If you remember, when we are so far we had calculated all three parts of A, B, C of problem, and we just want to revisit our problem. When we size a diameter of our bolt, we do that based off our bolt shear. By shear we means when we started to calculate our diameter of 28 millimeters. If you remember, the very first equation we used was shear, and then which later on we checked it for bearing stress, which if you remember it was 240, and which is less than allowable bearing stress, which is 350. And we already talked that if, and that was okay. What if it's not okay? What if we have like come with a numeric value of 400, which is definitely higher than sigma bearing? Then we need to recalculate our diameter, this time not based on shear but based off bearing, because the maximum is controlling. So but when our shear gives us a numeric value, we checked it and that was okay, problem is done. But if you calculate a diameter based off shear and then double check the bearing capacity and that's bigger than this one, you have to recalculate the diameter. Thank you. We'll solve more problem in stress and strain.